Greetings everyone, and welcome to this second session of the Pixapalooza webinar. We're very happy to see that so many of you could make it back to join us today as well. And the topic of today is going to be augmented reality, how to use it and how to push it to its limits. So before we dive too deep into the topic of augmented reality, it's important to understand what augmented reality is. The main way we differentiate between, well, there's many ways you can combine video with graphics in Pixitope and most other post-process pipelines and virtual production solutions. But the main differentiator, as we tend to describe it, is either you have a talent on a green screen with graphics with a graphical world or a virtual set that you put your physical talent in. Those are what we typically call virtual studios or VS. On the other hand, AR is when you have a video plate or a video feed where you wish to enhance the video or inject graphical elements on top or tucked in on top of the video. This is what we call AR, and that is going to be the topic of today. So before we start diving too deep, a brief introduction as same as yesterday. My name is still Frank Daniel Moendijk. I am a senior product specialist at the Future Group, where I've been working for the past 3 or 4 years. I think that's really all the time we should spend on that. The schedule is the same as yesterday. So we now made our way up to Tuesday, where we'll be covering the basics of AR. We're going to be looking at different ways of setting up a complex AR composite, including, but not limited to, holdouts, shadow catchers, light catchers, as well as how to get in photorealistic reflections while using augmented reality. Before we wrap up the session with something a bit exciting and interesting, just to keep us all on the edge of our seats, virtual characters and how to control them. Okay. So, somebody needs to mute their microphone. If you could get on that, Minus. Thank you. So, before we dig too deep into the technical side of things, let's just talk a bit about the session today. It's going to be a bit more relaxed than yesterday. We are going to do a slow step-by-step walkthrough on how to do things within Pixitope from start to finish, with the assumption that some of you might not really have spent any time in Pixitope before. So there's no need to worry. We're going to take this nice and easy and slow. It is also going to be a slightly shorter, more laid-back session than yesterday. Before we dive into Pixitope and start making our first set, let's dissect the scissor reel we just played and take a look at what AR can actually look like. AR can and has been used in countless different ways, typically used for things like scoreboards, election graphics, graphs, info, and all kinds of other infographics for that matter. You can use it to visualize esports data, like having 3D models of game maps from different esports events physically present in front of your casters, as well as any other kind of data visualization, from weather to, of course, election graphics to any kind of data you can feed into Pixitope. It's also used for things like set enhancing or just full-fledged AR productions, like the still we are looking at from last year's Super Bowl, as well as particle effects, particle enhancers, which was heavily used during last year's Eurovision. And of course, these full-on stage show centerpieces. So this is also AR. This is also AR. Some of the things we're covering today are how to achieve effects like not just having an AR element, but actually having an AR element able to cast shadows and interact with the physical world. As you can see here, when this AR Raven is flying in, we can see the subtle shadow being cast onto the field. This is among all the things we'll be covering in great detail today. So without further ado, let's dive into Pixitope. Now, something that quite a few of you asked yesterday is why we keep bouncing between director and editor. It's just worth mentioning that in a typical artist setup, especially if you are going to be working with the Pixitope director and the Pixitope editor on the same machine, we typically will always have a two-screen or two-monitor setup. So you can have director on one monitor and the editor on the other. Here, of course, we're using the other monitor for something else, so we don't have that luxury. So we just have to be tabbing between the interfaces instead. So here we have an already set up AR level, which we've spent far too much time looking at as is. So we are going to start with a clean slate. I'm going to go into my developer folder inside of Pixeldope, and we are going to start with a completely new level from scratch. Now this folder is a bit cluttered, so let's go ahead and make a new folder as well. Let's call this AR session, and here we go. If you're wondering how to access the developers folder, if you're trying to follow along in your own installation of Pixeldope, given that you have an early evaluation license, to find the developers folder, you will have to go to your content browser. In the bottom right, expand the view options and ensure you have show developers content enabled. So now that we are in our new developer folder, we can go ahead and make a new level. And we are just going to go ahead and open this. And now we are starting with a clean slate. This is what an empty level looks like within Pixeldope. Notice that the world outliner is already populated by these 4 Pixeldope specific actors that we briefly covered yesterday. We are now also going to set up our camera from scratch, just to ensure we do everything with the assumption that we are starting with a clean slate. So we are going to jump into Director. We are going to ensure we are in our Setup tab. And we are going to pretend that the only thing we've done so far is create a project, launch it into a new empty level. The first thing you have to ensure is that you will go to network and ensure that your data hub is running. You will not really get very far without one, at least if you intend to use the director. We ensure that we have a camera tracking server running on our local machine. If there's no such server running, simply hit add camera tracking server to ensure it's up and running. And then we're going to go ahead and add our camera. Now we already have the AR camera set up, but we're going to go ahead and do this process from scratch instead of covering it as briefly as we did yesterday to ensure we know all the steps we need to take to get our AR production up on its feet. So we're just going to add a camera system called AR camera. We are not going to set the film back because we are not going to be heavily reliant on defocus. We are not exactly using a telelens here. And then we're just going to move on to tracking. Now, briefly examining my camera, I can tell it's using a Moses mechanical tracking system. So I'm just going to go into my camera tracking protocol dropdown in the tracking menu and click Moses F4 1.7 mechanical. We also, of course, support their optical system, their star tracker. But for now, we're going to go with mechanical. Now I get a handle a pop-up telling me that I need to assign a tracking server to this particular camera. So I'm going to go ahead and assign this tracking server. We're going to wait a second or two. See, it's actually probably not going to behave. Yeah, so we are actually at this point, we are not going to see data. The reason for that is you will not be seeing tracking data coming in or going and being used until you've finished this setup process. This is actually very important to keep in mind. In case you get to this step and you're not seeing tracking data and you're wondering if you did something wrong, just make sure you finish your configuration before you start debugging. So we are now going to also ensure that we are using the correct lens file for this camera, which is typically something you need when you're using mechanical tracking systems. I believe the lens file is going to be this one. I'm getting a thumbs up from my partner in crime over on the side here. So we're going to go ahead and use this particular lens file. We're going to use focus distance, distortion, all the good stuff. There's nothing here we really need to worry about turning off. Next up is I'm going to need to set the video input output. So this camera that we just made is going to be used for AR, which means that we are not going to be needing the keyer, which means I shouldn't be using internal keyer as input type. It should be input camera. It already has the correct video input format, but if I want to change it, I could easily go to this dropdown and select progressive, or progressive 50, 1080p 50, if that was what I wanted to use, which it is. I'm also going to stick with Rec 709, which is fairly common in a lot of broadcast cameras. And I will not need to create a new media output. There already is one, but we can go ahead and recreate that from scratch just to see the steps. Add media output. You can see now that I just lost my output on the side because I deleted the output. Let's recreate the media output. And within a few seconds, we will not actually see it come back up because we first have to do a routing, sorry. So you can see we have a yellow dot here. This informs us that we have not yet completed the routing step. You would also see these in these other different tabs if there's something that is missing or something that we need to be warned about. Yellow means that you might have missed a step or something might be misbehaving as a warning. Red is a straight up error. If something has a red dot, that's something you really should take a cursory second glance at. So now that I am in my routing panel, I'm just quickly going to go ahead and route my signal. We're not going to use this old camera. We're going to use a brand new AR camera. There we go. That is on SDI 1, I believe. And we can go ahead and now check our tracking. Oh, no, we cannot. We have to add our output first. So we add our output to 3. We're actually using this output in different places. So I need to send this output to both spigot 3 and spigot 4. But you can easily take one signal and feed it to multiple different outputs on the fly. There we go. So we can see now we saw some flickering on the side, but the screen is still black. And that is, if I had to guess, because the scene itself, as you can see, is black. There's nothing in here. If I were to, say, pull in a cube from the Modes tab, where you can find all basic actors within both Unreal and Pixeldope, as well as a directional light source, and we were to ensure that this cube is somewhere in front of our camera, we can now see that we have live SDI feed coming out. Yes. So tracking. Now we should be seeing tracking data, and the reason I'm actually not seeing it is because the port is not correct. The port should be 1100. That might be in use by this previously made camera. So let's just ensure we don't have any conflicts. I'm just going to delete the previous AR camera setup because we basically just retraced our steps anyways. There we go. And then we'll go to tracking and ensure that our port is set correctly. And now, the moment I enter the port, we are now seeing tracking data coming in. And jumping into Pixeldope, we can see the tracking data represented in the top right corner. Very, very handy. So the last thing we need to do is ensure that we have set the correct lens data or the zoom encoder range, the wide and the far and close values for both zoom and focus. Do we happen to have those values noted down somewhere? No. In that case, we'll just have to do this from scratch. So we are going to go ahead and enable all screen messages. Actually, that should be enabled by default. Let's instead jump into live. Let's pull this over on the side. So what I'm going to be looking at here is basically here. When you are in the editor, you're getting in live tracking data, you'll be able to see your zoom encoder values and your focus encoder values. So the process here of getting the correct range is going to be that you'll go to your physical camera. You'll be pulling first your zoom all the way to minimum, inputting that value, all the way to maximum, inputting that value, and doing the same with your focus. So we're just going to go ahead and do that right now. Could you pull the zoom all the way to one end? Just hold in the zoom, it's all okay. So you can see now that our max, let's see if we can get the value here. So you can see the zoom minimum value is 80. That's probably going to be a zoom wide. I'm going to add a little bit to that just because I like to have a little bit of padding to my encoder values, just so we don't ever go out of range. If you could pull the zoom all the way to the other way, so we can see we're zooming in, and the max value is pretty close to what we had by default. It's a bit higher, it's 65,470. So I'm going to put that at 65,500. And now we're going to go ahead and do the same thing with focus. can see we're now pulling focus all the way far. So that's going to be a focus value, sorry, all the way near. That's a focus value of 10,000. Surprisingly round number. Now pull it the other way. That's all the way. Okay, interesting. So that's going to be a far value of 30. Very cool stuff. We are now going to go ahead and disable our screen messages just so we don't have the screen clutter to deal with. Oh, sorry, I realized I did that off screen. So the console command to quickly get rid of or enable debug on screen is disable all screen messages and enable all screen messages. These are things you can input either in the output log within with Pixel Editor. If you have a console button bound, you can also access the console at any time. Let's see here, sorry. The way you access console is going to be with an US keyboard using tilde, but sadly tilde doesn't exist on Norwegian keyboards. So if you need to be able to access console when you're live or whenever at any given time, basically, you will have to possibly rebind the default console button depending on where in the world you are. I like to rebind it to insert. So I'm just going to head on into edit project settings. I'm just going to search for console, and I'm just going to rebind my console button to insert. There we go. I'm also going to go ahead and bind that button in our project settings, our editor preferences as well. So here, sorry, not insert, console. So here I'm going to rebind show console and open console command box to insert. The reason I have to input this in two different places is because one of these hotkeys is used when you're in the editor, the other is used when you're in live mode. So now if I go into live, I can anytime access my console where I can type in any kind of command. I know there's quite a few of us that gets a bit nervous when we start seeing people pull out console windows, but rest assured the console is not just incredibly powerful, but also very easy to use. It's very easy to dig around in the console and find the specific render features you're looking for, even if you don't know specifically what that render feature is called. For instance, most profiling tools, which we've also handily exposed in the optimization tab, can be accessed through console using the stat command. And you can easily filter through the different performance tools or stat commands by just hitting the up arrow. As for render features, I could also hit R for render, dot, and then we'll be seeing every single render feature that we can adjust and tweak on the fly by just going up. This is also a context sensitive menu. So if I know I want to do something with my shadows, for instance, maybe I want to debug my shadows, maybe I'm ray tracing, I want to increase or decrease the samples for my shadows, I can just start typing shadow, and now I'll find every possible operation I can do with the shadow handily filtered for me using the console view. So again, the console is very powerful. Please do not be nervous of digging into it because it will, in the long run, save you a lot of time and headache. Okay. So now that we've set our zoom encoder wide and far, as well as our focus far and near, we've set our video input output and our routing, we are now more or less done with our technical setup. The only thing left to do is to enable AR within our level. So we're going to go into our Pixeldope editor. We're going to go to our world settings. We are just going to go ahead and search for AR and hit enable AR. Just like that, we are now, as you can see, outputting AR on the side here. So, very cool stuff. And at this point, we are basically live. Let's see. We're now in a live AR production. Just give me one moment here. Okay, so I'm getting a comment that my far focus might be a bit incorrect, so we're just going to try a different value. Okay, like so. Okay, so about that, I had a far more keen-eyed colleague than me observe that I've shuffled my focus values, and I simply had to switch them around. So what we've done at this point is in the director, we've done our initial setup, we've configured our camera, we've done our tracking, we've done our routing, and then we created a new level and we added a cube and a light source and enabled AR. At this point, we are live. We have AR set up for all practical purposes. If my colleague over here just wiggles the camera, we can even see that tracking is coming in and everything is sticking rather nicely. We're very lucky we don't even have to set sync. We could go ahead and set sync by going to the calibration sync panel. If, let's pretend now that we had more of a delay between our video and our tracking. Could you possibly wiggle it again? So as we can see now, hopefully even on our rather sluggish webcam out feed, we can see that our graphics are not in sync with our video. This is a very typical situation. This is what you're most likely to see whenever you set up a virtual studio or AR for the first time, because you have to ensure that the packets for your video input is synced up with your tracking packets, which, given that they're completely different pipelines, is rarely the case out of the box. The easiest way to align this is to either do some snap zooms or snap pans on your camera, which means you just do some jerky moves, start, stop, start, stop, start, stop, so you can quickly see if something is out of sync, and then you keep adding or reducing delay in this interface to ensure things are linked. So we could just use some hard snap pans. So we can clearly see here that our cube is lagging behind the video, which means that we have too much tracking delay or too little video input delay. So we could go ahead and add video input delay. We can see that our cube is still lagging behind, so we keep adding video packets. So it's getting better, it's getting better. And just like that, we are now completely synced up. However, having 12 and 11 frames, or almost a fifth of a second, actually a bit more than a fifth of a second, is not really ideal. So what we can do here, instead of saying 12 and 11 frames, we're just going to set this to 2 frames and 1 frames. So if you do the wiggle again, there we go. It's much, much snappier. A clap test would confirm this, but we still also have the same sync. Yes. So the next thing we have to do is we can see that our camera is on the ground. Okay, cool. I'm just having someone remind me of the values here. The reason the camera is on the ground is because this camera is a tripod. It's a mechanical tracking system. So the tracking data doesn't actually tell us anything about the tripod itself. That means that you actually have to pull out your handy measuring tape. You have to go over and start measuring your physical tripod or jib or crane or whatever have you. In our case, we have a tripod. We already measured it, so we know how far above the ground it's supposed to be. Speaking of the ground, let's just pull in a plane from our modes tab, just to ensure that we actually have a floor to look at. We are going to zero out the transform for the plane to put it in 0, 0, 0. We are just going to scale it up, which is going to give us a nice floor to look at. So here you can see the camera's on the ground. So now we just have to go ahead and input some offsets. So the way we do that is under the director camera tracking interface, we can go to camera mount, and we have a mount setup. So we're going to choose the mount setup, which is here at tripod. And the offsets we're going to be using is the height, or basically the base to the pivot point, is going to be 118 centimeters. There we go. As you can see, the moment I input this, the live output feed looks a lot better. We're also going to need some offsets for the actual bracketing of the camera. That's going to be a Z value of -21. I believe that's plus, sorry, yeah, of course. as a positive value. And the X value is going to be 10. We also have a handy diagram here showing you what these values represent if you're having a hard time figuring out what you're actually trying to measure. This also pertains to the calibration tracking panel. If you're unsure what any of these values actually mean, we have diagrams explaining exactly what you are offsetting or adjusting, whether it's yaw, pan, or tilt, and whether it's on the mount itself or the actual camera. And the same thing for our lens offsets and our CCD offsets, explaining exactly what it is that you are offsetting. So, jumping into live, we now should have our camera correctly lined up height-wise. Is that correct? We don't need any other offsets?
Yeah, for the basic settings.
Very cool. Okay, so next thing we have to do is start blocking out shadow catchers and basically start populating our scene. We've now set up AR A to Z, and now we just need to make it give the AR purpose, give it some graphics. What we have to do is populate our scene with graphical elements. We have to light those elements. We have to ensure they're reflecting correctly, casting shadows correctly. And then if we want to interact with them, we have to set up some kind of logic, typically blueprint-based logic, allowing us to interact with the graphics, trigger them, move them, spawn particles, fade things out, fade things in. And basically everything you can think of has to be done with some kind of programmable logic. Before we do anything else, we can look at a way of easily confirming if our tracking is more or less sound. Yesterday we briefly covered that we have some useful calibration widgets. The way you would go about using these is, for instance, the calibration columns. You would simply pull one into your scene, as seen here. You can hit the end on your keyboard to snap it to the floor. Very useful hotkey. I'll do it one more time. End. And we can then slide this calibration element to an easily referenceable point in our physical set to ensure that as the camera moves, things are tracking correctly. I'm going to use the corner of the billboard over on the side here. Notice that I'm not even looking at the editor as I'm doing this. I'm simply looking at my VSWIG output, allowing me to easily align this element without needing to constantly jump in and out of live mode. There we go. So this cone is now lined up with an easily referenceable point, as you can see. This is a very useful utility when you're doing things like verifying your lens distortion, or if you're moving around with, say, a Steadicam to ensure that, let's say, your floor is at the right height. We're very lucky here. We're using a PTZ, which is a lot more forgiving, but we can go ahead and move the camera to see how our tracking sticks. So we can do, for instance, a slow pan from side to side all the way. Keep going, just all the way. So we can see that we have a little bit of slippage. This could be caused by multiple things, but we know for a fact that right now it's because we haven't properly calibrated this lens. It was set up in a bit of a hurry. So the slight tracking slippage we're seeing could easily be remedied by just doing a second pass on our lens calibration, which we are just not going to worry about this for demo purposes, but that's how we would fix it in a broadcast setting. So let's go ahead and pull our floor back in. So one of the purposes of having a floor or a floor plane like this is so you have a shadow catcher, which, if that's a term you haven't heard of, think of it as an invisible geometry or invisible object that is still able to receive shadows. The reason we use this is because it allows us to generate virtual shadows to match physical shadows cast by physical objects. Now, if I could pass you to carry in the cardboard boxes and just put them on the center of the field. So you're just going to get in some new elements. While we do that, I'm going to right-click the plane and convert it to an AR shadow and reflection catcher, which you can see immediately makes this plane invisible in our output. So if we bring in our video feed, I'm just going to bring it in the editor view from the optimization tab, just so I can point at it with my cursor. So it's just going to be optimization, input video fill. So you can see we now have some very handy little cardboard boxes. And as you can see, these being physical real cardboard boxes in front of a physical spotlight, they're actually casting shadows. They're actually casting two main shadows, one towards the right here, the strongest one from my strongest light over on the side. There's also another light off screen behind the camera casting a shadow this way. In order for us to cast these same shadows in AR, we need to replicate that light scenario. We'll be doing that correctly in a minute, but for now, let's do it on a sort of a more high level. So we're going to just pull in a geometry, for instance, a cylinder. And we can see that our cylinder already has a shadow. In case you're wondering where you can see that, you can see it, of course, here on the white plane. You can also see it on the webcam output feed on my side, where we can see that there's actually a shadow that looks like it's lying on the physical floor. The reason for that is I already sneakily went ahead and converted this plane to a shadow catcher. In order to convert any geometry into these kind of utility objects within Pixeltop, all you have to do is select the geometry, right-click it, which gives you a lot of useful context-sensitive menus. But under the Pixeltop tab here, we can see we have a few convert utilities. We can convert something to a foreground element, a translucent element, a Virtual Studio floor element, a holdout geometry, an AR shadow and reflection catcher, an AR light catcher, as well as an AR ambient occlusion excluder. The elements we are going to be covering today are going to be holdout, AR shadow and reflection catcher, light catcher, and the ambient occlusion excluder. I suppose we'll also, to a certain degree, will be covering translucent and foreground. So if I were to convert this back to foreground, that just means I'm saying this object is a standard AR geometry. There's nothing special about it. Every geometry you spawn will be a foreground element by default. If I again right-click it and change it to a shadow and reflection catcher, it becomes invisible in my output because it's now an invisible object only meant to receive shadows. Inversely, if I were to convert this to a light catcher, it actually catches light, and since we have a uniform directional light, we get light everywhere. Not very useful right now. It's very useful when we start messing with localized spotlights, but for now, let's stick with the shadow and reflection catcher. So converting something to light catcher also changes the material of the geometry. So I'm just going to go ahead and change the material back to clear it out. There we go. To do that, you select the geometry, you go to the details panel, down to materials, and you just change the material back to whatever you had before. Okay. In case you're wondering exactly what all these conversion things actually do, under the hood, they change what is called the stencil value of our different geometries. Stencil values is how we identify the purpose of different geometries and how we filter between them and use them for different things in our render pipeline. So you can see now that this cylinder and this floor element have different custom depth stencil values. Generally speaking, you shouldn't really be setting these manually unless you really know what you're doing. I'm just showing this in case you wonder exactly what this changes in the object attributes. Okay, so now that we have our handy little cylinder here, we're going to go ahead and add two light sources instead of one. And instead of using a directional light, we're going to go to the lights panel and use rectangular lights instead. Because as we can see, if we were to pan the camera to the left, the light source is a rectangular spotlight. So here we now have our rectangular light source using the fairly recently introduced rectangular light actors in within Unreal. I'm going to go ahead and give it dimensions which actually match the physical light, which I believe is going to be a width of 21 centimeters or units and a height of 97 centimeters. We are also going to adjust the barn door angle of the light because we can see we have flaps on the physical light. So I'm just going to try to match that. What I should do next is go in and try to measure out the position of our light source. An easy way I can actually do that right now is, for instance, just create a cube with the same resolution. So just do 0.21 by 0.97. So this cube now more or less has the same dimensions as the actual bulb within this fixture, a light fixture. And I can just go ahead and slide that into place. Shows, of course, is above ground. I'm going to rotate it. Again, I'm now looking at my live output feed as I'm positioning this object into where I believe is going to be roughly the correct position. The reason I'm able to do all of this from a singular point of view without needing to move around is because we are confident in the fact that our tracking is good and the fact that our camera is positioned correctly and that our dimensions are measured correctly. So now that I have this object positioned, we can see it lines up pretty well with the physical light. I'll just go ahead and use this to now line up my area light actor. It's a bit hard to see what I'm doing because everything is so dark. So I'm just going to change to unlit mode so I can more easily see what I'm doing. The hotkey to do that is Alt-3, but more reasonably, you can do that from accessing the View Mode tab in the top left of your editor viewport and change between all the different basic view modes within Unreal. The easily accessible ones are accessed by hitting Alt-2 to Alt-6. These are wireframe, unlit, lit, detail lighting, which basically removes every material. As you can see, we get rid of the checkerboard, we just get the normal map and everything with the same white diffuse look. And then there's lighting only, which removes normal details, which is good if you just, especially if you want just a clean render, if you see in for things like a BTS roll, where you want to see things before they have materials applied. Alt 7, 8, and 9 are reserved for more complex debug utilities like light complexity, shader complexity, and so on, which we will not be diving into those right now. For now, let's jump back into unlit and position our light source. I should probably go out and use my measuring tape to ensure both the position relative to the camera is 100% accurate, as well as ensuring that the dimensions are 100% accurate. But for this brief demo, I think this should be more than sufficient. So we can see now that looking in our output, the light seems to be coming from pretty accurately the correct position. I'm holding Alt and dragging the light source. I could also select the light source and just hit Control-C and Control-V to copy paste it, as you can see. And I'm going to take the copy and move it to the right-hand side. So this light is going to be left light source. I use F2 to quickly rename them. You can also right-click and just hit rename somewhere. Don't even remember where that is because I never use it. Oh, you can just double-click it, sorry. Or just use F2. Right light source. Oh, there we go. Notice that these actors in the world outliner have these colorful or yellow and orange dots next to them. These are actually very, very important. What these tell you is the mobility setting of the actor. For geometries like this plane and this cylinder, which has no dot, this tells us that these geometries are set to be static. This means that these actors cannot receive baked lighting. They can also, by default, not be moved during runtime. If I were to try to move these when I'm in live mode or use a blueprint to move them, it would simply give me a lot of errors in my output log and not a whole lot else. If you wish to be able to move geometries, ensure that they are set to movable. Changing that in the details tab gives them an orange dot telling us they are movable. As for light sources, we can see they have a yellow dot, which is stationary. Stationary is a bit more complex. It's kind of this sort of in-between mode between static and movable, allowing something to receive or generate baked lighting, but still be moved during runtime. That might not be 100% correct, but you can get 100% correct breakdown if you just hover your mouse over the button. But we are just going to use fully dynamic lights, so I'm just going to set these to be movable. Notice that this also changes the gizmo or the tooltip icon for the light source. Movable gives them this movable icon. So our second light source is pretty weak. I'm not going to worry too much about lining it perfectly because I know it's angled roughly this way, tilted a bit up. It's slightly below our camera, and it's about a meter off to the side. There we go. You shouldn't, of course, be this haphazard during your productions, but for now, I think this will suffice for this rough blockout. I'm also going to make this light source a bit stronger, trying to match the lighting I'm seeing on these boxes on the ground, whereas this light source might be a bit too strong. We can also see that there's probably a bit of color to this physical light, whereas my virtual lights are currently completely white. So I'm just quickly going to go check the Kelvin on the physical light, and we can input that particular value. Or actually, could I bother you to do that? There's multiple ways you can color lights within Pixeltop. You can, of course, go ahead and change the light color by just giving it a color. Simple as that. But if you want to match a physical spotlight, you will have a much easier time if you just try to replicate the actual color temperature. What was the color temperature? So color temperature for this was 3,300, which gives us a pretty warm light. I'll go ahead and do the same thing over here. And looking at the glance, I can tell this, of course, looks far too hot for me. I could fix this by using the grading suite within Director, or I could just freehand it and say that I'm going to dial this temperature back up a little bit until we have something which looks a bit more reasonable. There we go. So it's still slightly warmer, but now it's looking more to be in the same realm of existence as our boxes. We can also see that we don't really have any really strong visible shadows here. The reason for that is probably going to be, so you can use the attenuation radius to set the range of your light. I'm just going to show the range is long enough. And now I'm going to full screen my editor, and I'm going to jump into Director and use Director to fine tune my shadows per light using the production tab. You could also do this in the editor, but it's nice to do it in the editor so you have a full screen view as you're working. So it's nice to do it in the Director so you have a full screen view of the editor as you're working. So I'm going to go to Composite, which is where we can find our shadows. You can see that we have some settings tucked away at the bottom, which means this display is a bit too small to contain all the elements. So I'm just going to hit Control- once to scale everything to fit the interface. Then I'm going to go ahead and first change my left light source and just dial it in. Before I start dialing the individual light sources, I will just apply a universal override to all the light sources, which is like a global shadow intensity. Just see if I can get some shadows in here. Setting this pretty high might be necessary for area lights, which behave differently from other light sources. But setting this to 10,000 gives us shadows which are looking pretty good. I can then go ahead and fine tune my respective light sources if I so choose. But I think I'm going to be happy just fine tuning this for now. There we go. And I think I'm pretty happy with that. I'm also going to go ahead and move the cylinder around a bit just to see how the shadows look from different positions. So I'm going to go into the Adjust Object panel in the director. We're going to go ahead and go to Objects. We're going to grab our cylinder, and we're going to just quickly shuffle it around. So I'm going to, I'm going to Mobility, and I'm just going to be hitting these buttons. So as you can see, as we shift it around and pull it to the right, we can see that we have a shadow here coming from the other light source, which seems to stick very closely with the shadow we're seeing on the left here. Pulling it back on this side, we can also see the shadow on the right-hand side seems to be pretty bang on with the shadow we have from the boxes. Very nice. But we are also, by doing this, we can easily identify a problem. We can see that the shadows from our cylinder is overlapping the boxes, which of course is not physically correct. The shadows should be behind the boxes. Even worse is if I move the cylinder behind and try to tuck it in on top of the boxes or behind the boxes, the augmented reality is sorted in front, which doesn't really look good at all. Now, most of you might already know that AR typically will always go in front, especially when you're talking about people. People will always sort behind AR, simply because you can't really key people without a background to key them against, meaning you can't really generate what we call a holdout or a mask for moving objects. Static geometry, however, is a completely different use case. These boxes, which I happen to know are 19 by 19 by 19 centimeters, can easily be occluded within Pixeltope. The way we're going to go ahead and do that is by just dragging in a geometry. If these were not boxes but a more complex shape, then we might want to, of course, create a 3D model instead. For instance, you might see the orange chair in the back, which we were casting shadows on earlier in the first scene we had of today. The reason we are able to cast shadows on the chair is because we used photogrammetry and some modeling to recreate that chair in 3D and importing that model into Pixeltope, allowing us to use it as a shadow catcher. Shadow catchers don't have to be just floors. As for these cubes, I'm just going to create a new cube actor within Pixeltope. The default Unreal cube is 1 by 1 by 1 meter. So a scale of 111 means that it's 1 by 1 meter. Since I know that I'm going to need 19 centimeters, I'm going to set the scale to 0.19. We're going to hit end to just drop this on the floor. And I'm going to be looking at my output as I'm quickly lining this up with the cube on the ground. Pretty bang on. You can see we have some slight rotational issues. So what I'm going to do is I'm going to use the middle mouse button at the center sphere of my gizmo. I'm going to hold V to snap it to the corner of my cube. There we go. I'm going to right-click the cube and save the pivot, simply because I find it's going to be easier to rotate it when I already have a single corner locked down, as we can see here. Very nice. Then we're going to stack the next cube on top of this. We just move it up and hit end. This cube on top, we are going to line up as well. I'm just going to temporarily hide the bottom one while I do this top one, just so it's easy to see what I'm doing. There we go, good enough for live. And then we do the last one up on top. You might wonder how I'm hitting the gizmo, how I'm actually interacting with this without actually touching the gizmo. I'm not a huge fan of using gizmos unless I have to. So luckily there's hotkeys to move things around without using the gizmo itself. You can of course click and drag these handles. You can use W, E, and R to change between scaling, rotation, and translate. I just use the respective hotkeys, W, E, and R. And you can also use Control plus left mouse button, right mouse button, or both mouse buttons at the same time to move, scale, or rotate something along the Control left, which is the X-axis, Control right, which is the Y-axis or green axis, or using Control on both mouse buttons for the Z-axis. Just a nice little hack to save you some fumbling around trying to reach the gizmo, if that is your thing. Probably shouldn't be moving this up because we do know that the scale is correct. But even if you measure something out and it doesn't line up, sometimes you do have to make amends because the most important thing is that the holdout holds. So there we go. We now have our 3 different cubes. I believe this top box might be slightly bigger for some reason, so I'm just going to offset this. And now we just select all of these at the same time. I'm going to hit Control G to group them together, just so I can select them together at any given time. And I'm going to right click and convert them to an AR, shadow, and reflection catcher. So these are now gone, they're invisible. But if I go into live mode again, I keep moving my cylinder, we can now see that we've had a very, very nice development. Our shadows are now sorting behind the cubes. And if I were to move these in front, we see the shadows on the cubes. Obviously, these shadows are a bit harsh, so we could fine tune that a bit. For now, I'm just going to go into composite. We're going to go into our shadows. And instead of worrying too much about down this in 100%, I'm just going to say that I'm going to give the shadows a max value using the ambient offset. And just pull them up ever so slightly. We can also use Luma mask to ensure that we don't get doubling up of shadows. This is handy if you have an AR object that is casting a shadow, but then you have a physical object casting a similar shadow right next to it, and you don't want those shadows to overlap. A typical use case is if you have a sunlight shadow, which is then bleeding into somewhere where the sunlight doesn't reach in your video feed, then you might want to use Luma mask, which is actually sampling the plate to ensure you don't get a doubling up of your shadow. We can also now, we can see that we need to fine tune our holdouts a bit, but we're just going to leave it for now. We're going to go back into adjust object. And as we shuffle our cylinders in, you can see that we are even able to tuck it neatly in behind our boxes. Very nice. Okay. Now we could go ahead and keep doing this process for every remaining actor in the scene. But luckily for all of us, we've already gone ahead and done that, just so you don't have to watch me meticulously measure up all the back billboards, the back wall, the light fixtures, and so on. If I just go to Pixelpalooza Blueprints, I've already made a pre-assembly called, what did I call it? Let's see if I can find it by just filtering by BP. I believe I called it Holdout. Houston, we have a problem. Okay, I'm going to quickly bounce back into the level and just see what I actually called it. Oh, I see that my blueprint might have been saved. So I'm just going to take this already existing pre-measured holdout geometry. I'm going to select all of it. There we go. I'm just going to take all these different bits and pieces. We're going to hit blueprint at the top and convert it to a new blueprint class. I'm just going to put that underneath Pixelpalooza blueprints, call it BP holdout. Actually, it's not a holdout, it's a shadow catcher. There we go. Ah, yes, I probably forgot to save this earlier. There we go. Now we have our new blueprint and we can jump back into our level. And again, the reason we're doing this is just so we can use something I've made before the demo session, so this session doesn't run over as long as yesterday. Here we go. We go ahead and pull in our holdout. Just ensure it's lining up with the floor. We can actually see that the center of this blueprint is not floor level, which can be a bit annoying. So I'm going to open the blueprint itself. The blueprint is, as we briefly covered, a collection of both visual programming utilities and nodes, but it is also a collection of actors. Collection of actors, which you can see are not lined up with the floor. I'm going to go ahead and shuffle these up. Now, this doesn't have to be sub-millimeter accurate, just try to get this as close as you can. So there we go. Now the floor is lining up with the floor of the blueprint, which means that I can now take this blueprint, snap it to the ground, and it's going to line up nicely with everything else. Now I can't see that as I move it around, I can't see it in my output because it's already set to be a shadow catcher. So I'm going to right click it instead and convert it to translucent. Doing this makes it semi-transparent, allowing me to now very quickly line it up with my physical geometry in my set. See that here that we have a slight rotational offset to our world. And again, we do know for a fact that our tracking is a bit spotty due to our lens file and distortion, but I'm just trying to get it as close as I can. There we go. Now it's a bit dark in here, so we can also go ahead and pull in a skylight just to be able to see things for now. I'm just going to go ahead and choose a random cube map just to give us some ambient lighting, make it easier to see what's going on. There we go. That's pretty close. We will leave it as is. Now, on the topic of skylights, cube maps, and lighting in general, this has all been very superficially touching on the subject. But good lighting is actually completely essential for your augmented reality. One of the biggest mistakes you can make is take your lighting too easy or skimp on making your cube maps and making your reflection captures. Because what you basically need to be able to do is sample as much data from your physical world as possible in order to inject that into Pixeltope so you can have the same light and the same reflections show up on your virtual graphics as well as your physical geometries. There's many ways of going about doing that. One of those ways is going to be using one of these little bad boys, which is a 360 capture camera, allowing you to quickly and efficiently capture, well, do a 360 capture. This camera is a Ricoh Theta. I believe it might be a Model 5 or Model V, which is what we typically use on site for most of our AR productions to do our reflection captures or our HDR captures. And at this point, you're probably asking, what is an HDRI? What is a cube map? What am I talking about? So why don't we do a deep dive into what this actually means? So I'm sorry, but we do actually have some slides for today as well. So let's all buckle up and run on through. These are all courtesy of my colleague Øystein Larsen, who offered to do a thorough write-up on the process of generating a cube map from scratch. This is something that anyone that intends to do AR in real time using a reel should know how to do. This in particular is going to be a walkthrough on how to not just do a cube map capture, but also do a set reconstruction, which is sort of the next step up, where instead of just capturing a 360 light source, we also regenerate the geometry of the physical world so we can correctly ray trace based on physical distances between different objects, instead of having sort of a single point reflection capture, which is going to be the same no matter how you move your geometry around. We're going to cover HDRI captures using the Ryko Theta 360, which again is the camera we just looked at, this one here. How you merge these different images to an HDR, because our camera doesn't do HDR by default. We have to generate it with some a bit of post-processing, as well as how you measure and capture your set geometries, and how you finally project and bake these textures using EXR. And as we just went through, having a good digital twin of your location or studio is helpful in many ways, not just in terms of getting physically correct reflections and lighting, but also just because having a reconstruction of your venue will help you with blocking things out, planning camera shots, ensuring that things look to scale well before you actually get on site for the production itself. For quite a few bigger productions that we've done, we've actually gone or sent someone on site very early to do LiDAR scans or similar ways of reconstructing the physical environment, allowing us to have a 3D model to do all our planning and blocking out around. For Pixelstop, we specifically use these digital twins to catch shadows onto live surfaces, shadow catchers, as well as reflect our AR in real environments, using it as a holdout for AR moving behind real objects. Specifically for RTX, it localizes the reflections to a place in a 3D space. What this means is that instead of saying, here's my 360 sphere, and in that direction, there's going to be a strong light source. Now that light source exists in 3D space, and as our AR moves closer to this light source, the reflection from that light source becomes bigger and bigger instead of staying the same size. Because an environment map is just infinitely huge, sort of an infinitely huge 360 sphere around the graphics, which means that things don't change scale or size no matter how you move your graphics around. The Ryko Theta has a very nice multi-exposure mode, allowing you to put it up on a tripod and quickly do multiple stops with the push of a button. I have it linked to my smartphone, so I can just click a single button and then have pictures directly on my phone ready to be reviewed and used. Yeah, so you shoot from your phone. The newer Theta models shoots RAW. We currently don't really tend to use the newer models because we have a nasty habit of breaking or forgetting these cameras in different offices around the world, so they're never at hand when we need them. So we often end up having to buy new ones on site. But if you can afford, or if you're willing to use the more high-end Thetas, that's strongly recommended, because it supports full 5K 360 images. We recommend as many exposures as you have time and patience to take, generally speaking, but 8 to 10 with 1 to 2 stops difference tends to give pretty good results. You also should, of course, review the light setting scenario that you are trying to capture to ensure that your ISO values and your exposure is set in a way that makes sense. You also absolutely need to be using a white reference card or board to ensure that you're able to set the white balance when you start combining your final high dynamic range cube map. So these are the actual pictures I took 2 days ago from our physical set right here on a tripod. So you can see our exposure is going all the way from very low to very high. This is actually a bit low of a range because we can see the top we could have probably benefited from a few even higher exposure shots here at the top, just to help fill in some of the darks we're seeing here. As well as the lowest one, we probably could have benefited from having a bit more range on the 2 physical spotlights in our set, but it has proved to be sufficient. So what you do is you will open Photoshop. There is a separate combine functionality which allows you to combine. Let's see if I have Photoshop installed. Sadly, I don't have Photoshop on this machine, but there is, if you go down to a drop down, I believe it's under extras, there's a separate utility to combine multiple images to HDR. Which is the functionality used here. Yeah. So you can apply the camera raw filter, depending on your camera, to mid exposure of your image. Then you use the white balance tool on your card to ensure that you have picked the correct white reference. This filter should be applied to all the images you use in your HDRI creation process. Oh yes, sorry, this is the previous step. This should be done in Photoshop. This is the utility I was talking about, which can be located under File, Automate, Merge to HDR Pro. Just grab the folder where you have your images saved and just add all your images. You don't have to worry about sorting them with names or anything like that. The utility will do this for you, just by having the Attempt to automatically align source images checkbox selected. Ensure that you have 32-bit mode enabled in the next step, otherwise you will not be able to save this as a high dynamic range output file. And then you can complete the toning in the Adobe ACR suite. Yeah. So then you can go in, you can keep refining your mid-exposure levels. You should also paint out everything you don't want to see in your 360 image, including the tripod here at the bottom, as well as this card, which I had tucked behind this cable fixture on the wall over here. So you can see this is before, tripod and card visible, and afterwards, using autofill, we've filled those elements out. Resize this to a 4K square image and save it as a Radiance HDR image file. This can later then be imported into Unreal and will then be able to be used straight as an HDR image. And then you can go ahead and reconstruct your set as well using your 3D modeling suite of choice. Here we are seeing it being done in Maya. This could, of course, be a laser scan 3D model, or you can, in a simpler scenario like what we have here, just measure up and model things by hand. Then you simply create an unlit material and you use spherical projection from the point of view of where you put the theta or your 360 capture device, and you project your image out onto your geometry, as you can see having been done here. This geometry needs to have decent UVs, just so you have good texture resolution. Yeah. Ensure that you don't really have overlapping textures, like the ceiling behind your 3D models of the light fixtures don't need a doubling up of the same light fixtures in the texture, so those should be painted out. And then you can finally take these models and the textures and import them directly into Unreal. So you can actually see that we have this in Unreal. Look at here underneath AR Studio RTX Stream. Let's take a look at this right now. Let's also ensure that we are in Director, Setup General, that we have ray tracing enabled. Very good. Just ensuring that, yes, we have ray tracing on. So here we can see the final result of our set reconstruction, which is going to match one-to-one, more or less, with the physical set. I'm just going to quickly go ahead and temporarily make this an AR scene so we can have a cursory glance at it. This particular level has been set up as a sub-level, which means it's meant to be used in a parent level, so it doesn't have its own essential actors, camera tracking device, and similar. But I will just go ahead and temporarily recreate those so we can work with this scene. See here. I have a live output, so I can quickly just select all my geometries. Yeah, so I can see I have some offsets, which are mainly going to be caused by the camera root position, as well as the camera root orientation. But I can quickly go ahead and dial this in ever so slightly. There we go. Ensuring that now the geometries are in the correct place. So these are, of course, the project geometries, but the actual 360 image can also be visible in a skylight actor. We'll be covering this basic use case later. For now, we are going to take a look at why do we actually want to do this labor-intensive reconstruction process. And the reason is so we can use this geometry with ray traced reflections. As you can see here, as I drag in a sphere, I can give the chrome material to make it very shiny, basically make it a chrome ball. Let's actually set the roughness of our chrome ball to 0 to make it perfectly reflective. There we go. And here we can see the benefits of really doing things this way. Notice that as I move this chrome sphere closer to this chair, the reflection of the chair becomes bigger. Now, if I were to say do this using a more traditional Unreal workflow without RTX, but using, say, sphere reflection capture instead, which is a way of forcing in a 360 capture taken a particular point of view in your scene. Select the specified cube map, and we're just going to use our studio cube. So this is not the correct studio. This looks far more correct. Now, if I were to pull this in and disable ray tracing reflections, just r.raytracing.reflections 0, which will kill ray trace reflections. Let's see. Yeah. We can now see that as I move this chrome ball around, the size of the reflections doesn't really change. There's a little bit of warping from the point of view of the theta, but it's not very physically accurate. So you can see, despite me pulling this very close to this billboard, the reflection of the billboard is not correct. Inversely, if I pull this chrome ball close to this spotlight, it's not actually reflecting correctly. But if we go through all this trouble and all this headache of doing this properly, creating this set recreation, then as we re-enable ray trace reflections, you get these insanely more accurate reflections that will scale correctly as your geometries or your actors or your augmented reality shifts around in your set. So it really is night and day. It is absolutely worth doing, especially if you intend to aim for photorealism and taking your graphics to the next level. So let's actually take a look at this. Let's make our geometry invisible, because obviously you don't want this geometry visible as you're doing this. You want to hide it, so you're only seeing it in the ray trace reflections. So I'm just going to open the material and set the material parameter collection. So we have a value exposed, which allows us to quickly make the geometry invisible for a naked eye. I'll set this to 0. So here we can see that, let's actually move this using the directory so we can do this full screen view. I'll go to production, adjust object. I am going to go ahead and adjust the sphere, which I just created. I forgot to set the sphere to movable, which means I can't move it, but I can easily override that parameter from this interface by changing the property mobility from static to movable. So you can see here that as I move this around, the reflection of the banner becomes bigger and smaller. Could you do me a favor and zoom in on the chrome ball on the ground? I'm sure you set the focus as well. Yeah. Let me double check my focus values here. You can see that the focus, the depth of field for the graphic seems to be a bit incorrect, which probably is because I fumbled setting up my focus encoder values earlier on. Let's take a quick look. There we go. That seems to be, oh, that seems to be slightly more accurate. We are also going to go ahead and disable shadows. We only care about reflections for now. Oh, oh, that was actually not shadows I was seeing. I simply had this scaled incorrectly. So what we are more or less trying to emulate is basically the same reflections you're seeing on your physical chrome ball over to the side here. Yeah, I don't think there's a point spending too much time looking more at this. I'm certain the point gets across. If there's people are interested in trying to replicate this later, we can also go ahead and share this document with you so you can try to retrace these steps from the comfort of your own office space, or more likely in these days, from the comfort of your own home. Okay, so next up, now that we looked at how to set this up, we can jump back into our new scene and we can start populating it with actual graphics. So we are actually going to go ahead and jump into the scene we've been using up to this point, the AR backdrop scene. We don't need to save any of this. Where we already have spent some time lighting, dressing, and making things look a bit more snazzy. There we go. Could we go ahead and just give us a nice full frame again? Thank you kindly. All right, so first of all, before I do anything else, I am going to get rid of a light source here, which is not set correctly and casting gnarly shadows on the ground. Very good. And now this scene has already been populated with some graphics. So we are going to quickly go ahead and get rid of some of them and start thinking in different ways. I think we can probably lose this for now. Let's clear some space here along the wall. And let's start working on this from scratch. So what we have here is basically all our lights replicated using area lights, not just the left, right, and the right light, which we set up before, but we also here gone ahead and set up area lights for the ceiling lamps. So we are also seeing what I believe to be yes. So we have to ensure that we have ray tracing enabled. First of all, this set disables ray tracing by default. Just go ahead and enable that. And let's just quickly ensure that we are in the correct color space by going to Composite, General. So we should not be in video space. We should be in linear space. Notice that in my display here, as I go between video space and linear space, when we are in linear space, the colors might look a bit more out of whack. But that's simply as I covered yesterday, because we are not currently applying the output color conversion when we are in the viewport. So now that we have our scene up and running and ready to go, we can start populating it with some graphics. We've got them, we set up our lighting. The only light source we are missing is going to be our skylight. So let's go ahead and set that up from scratch. So this is basically what we had in our earlier blockout level before we had the skylight. We had our real lights and not much else. So the purpose of a skylight is basically to give you ambient or global illumination. Well, not technically global illumination, but an approximation thereof. It is giving you the overall directional light from at some arbitrary point in your scene, allowing you to sort of fill in a lot of these black darkened out spots where tangible direct light sources aren't reaching. So here we're going to go ahead and select our source for this skylight, which is going to be a specified cube map, and it's going to be the HDRI of the studio, which we just walked you through on how to create. Again, it's not going to be this studio cube, it's going to be, let me just find it again. It is going to be, there you go, the AR studio. Now, the next problem here is that we can clearly see that this is a 360 capture, which means it needs to have the correct rotation. Otherwise, we might risk that this chair, which is supposed to be on the left side of our studio, is being lit or being represented as if it's on the right side. The easiest way of ensuring that your skylight and your reflection captures or anything that relies on an HDRI is rotated correctly is by pulling in a sphere. We could convert it to a chrome ball, or even more simply, we could go to lit and just enable the reflections mode, which renders everything in the scene as if it was a chrome ball. By doing this, we can now take our skylight, and I can't really go ahead and rotate it because we are ray tracing our holdouts. So I'll turn ray tracing off for a second. And as you can see now, as I rotate my skylight, nothing happens, because this rotation has to be input underneath the skylight details panel underneath cube map, source cube map angle. You can also see that the lower half of the cube map is set to be black, so it's a bit hard to see. This is default in skylights within Unreal. The main purpose of having the lower hemisphere being black is so you don't get too much bounce light from below. So it's an approximation, but it's usually a good one to ensure you're not having too much light. Given that this is a chair and this is the back wall, we should be seeing a reflection of the back wall from this angle. So I'm just going to go ahead and rotate the cube map until I'm seeing the wall rotated correctly. Very good. I'm going to go ahead and enable ray trace reflections, and we're going to move on. So just like that, we now have our skylight set up. We can make it stronger or weaker simply by adjusting the intensity value. Try not to keep these too high. We generally find that values between 0.5 and 1 tends to work pretty well. So next step up is that we are seeing, unless we are in ray tracing mode, or even if we are in ray tracing mode, we're actually seeing some pretty aggressive ambient occlusion between our different holdout geometries. This is intended behavior, but sometimes it might be a bit too much, like we're seeing over here. I'm also quickly just going to go into my calibrate tracking panel in Director, just because I can see that some of my geometries are slightly tilted off, because as I created this new camera, I forgot to input some of our finer rotational offsets for our tripod. There we go. That's slightly more accurate. So when it comes to ambient occlusion, you have multiple ways you can deal with that. Sometimes, especially if you're not dealing with big environments, you could just go ahead and turn ambient occlusion off from the post-process handler, which means we are no longer looking at gnarly ambient occlusion anywhere. We could also selectively kill ambient occlusion by using what we call an ambient occlusion occluder. So you can, for instance, here pull in a cube and say that I want to selectively not have ambient occlusion underneath this wall fixture. So I'm just going to go ahead and cover that entire fixture with this cube. We are going to right click it and convert this to a ambient occlusion excluder, which makes it apparently invisible. Let's actually do this half and half so we can compare before and after. And now if we go into live, you can see that here on the right-hand side, the ambient occlusion is now gone. Whereas on the left-hand side, we are still seeing the ambient occlusion. And that is more or less the functionality of the ambient occlusion occluder. Same thing, if I move it over to the left, we are now lost the ambient occlusion here tucked under the corner, but we are still seeing it on the right-hand side. Now, let's go ahead and start populating our scene with some graphics. We could, of course, build something or import something, or we can just start digging through our project and pull in a few random bits and pieces. There's no real conversion or anything we really have to worry about. We can simply go ahead and start adding geometries. Like this clock fixture. Let me just quickly move my pivot so this is easier to deal with. This is obviously a part of a building used in a different level within this project. There's nothing stopping me from saying that I would like to have this clock up on my wall, meaning I can just go ahead, select it, position it, and slap it up somewhere on my back wall. I don't have to prep it in any further way. Simply by going into play, we are now seeing our area element in the scene. We can also go ahead and add things that have transparency. Let's see if we can find something with a bit of glass. That doesn't really look to be like transparent glass to me. So let's see if we find something more applicable. It might always be nice to pull in a few bits and pieces of foliage just to dress our scene up. And again, populating your AR is as simple as building any traditional set in the real. Once you have your actors, you simply pull them in and populate your scene. Granted that your shadow catcher is set correctly, your AR will composite correctly. Okay, let's actually go ahead and build a glass shader because I seem to have forgot to send it. Oh, here we go. So here we have the sofa table from the other Virtual Studio example scene that comes with Pixeltop, the Virtual Studio. Notice that this table has a solid base, the sort of twirly metal, but we also have what appears to be a transparent refractive glass tabletop. And if I play, we'll be seeing that this is not actually behaving as intended. The metal looks correct, but the glass surface is giving us some issues. This is probably partially caused by the material of the glass, but also because the glass needs a separate pulse process. Sorry about that. The glass itself needs a custom pixel stencil. It needs to be set to translucent. So now the right one is set to be foreground and the left one is set to be translucent side by side. And we can here see that the glass on the left-hand side looks a lot more correct. It is even correctly refracting the video plate through the glass. But we can see that in the process of doing this, we've accidentally broken the metal base. The reason for this is because a single geometry can only have a single stencil at a given time, which means that we can't have transparent and solid values or solid materials within the same object. But that's luckily easy to work around. We could, for instance, just take the geometry and copy paste it. Let the top be the table solid, and the bottom can be the table transparent. Ensure that the transparent is set to translucent and the solid is set to foreground. And then we are simply going to, on the solid, give it an invisible material for the material slot we're not going to be using. I can just go ahead and make that right now. Material M invisible. This is not going to be anything very abstract. It's simply going to be a masked material with an opacity value of 0, meaning it's always going to be invisible. So then we pull on the solid, we don't want to see the glass table. On the transparent, we don't want to see the legs. Now, if we jump into live, we can see that there's our glass behaving more or less as intended. The refractive nature of the glass is something you can use, but we generally try to avoid it just because there's quite a few hurdles you might have with extreme refractive values. So I could, for instance, go into the glass shader and simply set the refraction to either be disabled or to be using pixel normal offset instead. Exactly what that entails is something you can read about in the real documentation, but it basically changes how the refraction is calculated. Notice that this shader takes a lot more time to compile because transparent shaders are notoriously more heavy and complex within Unreal. While we are waiting on this to compile, I just want to give a reminder that please keep asking questions. We will answer all of your questions in plenum at the end of this session. If there's something that was unclear to you, it might be unclear to others, so it's in everyone's best interest that you please reach out. As this is coming in, could I also pass to you, Magnus, to go ahead and set up the light so we have a backlight for our AR? So I think we need to clear some space here because we are now ready to move on to the next step. Okay, so we now introduced a few bits and pieces of virtual graphics into a scene. Now, I wasn't really a huge fan of that wall fixture, so let's just pull in some other bits and pieces, and then we'll be looking at how to help compositing this in a clean way into our graphics. We already covered in great detail how to enable your shadows. But what about light? let's say, for instance, that we have a virtual spotlight casting light onto augmented reality objects, and we also want to replicate this light onto the physical world. You can see here we've added a bit of rock and foliage to give this more of a wilderness look and feel. Go ahead and re-add a little bit of foliage as well. And at this point, we might be able to say that this looks pretty good, but it's all a bit dark, flat, and dull. We want to light this in a better way. To do so, you could, of course, just go into your scene, go to lights, and drag in a rectangular light or a spotlight. For this use case, let's just use a very harsh, aggressive top-down spotlight. Let's actually search for a lamp as well. There we go. So we can actually have a lamp fixture emitting this light. Having randomly floating light sources hovering in space doesn't really look too good. Given that's going to be a directional light, let's go ahead and add a point light instead of a spotlight. The different light sources are, by the way, skylight, which is sort of a universal ambient cube map. There's the point light, which emits light in all directions. The spotlight, which acts as a cone of light with a easily configurable cone of effect, which also supports different light profiles and light textures. And then there's the directional light, which acts like a sun, applying non-scattering directional light from a particular direction. In orders of performance, the most performant light is always going to be the spotlight. The point light is slightly more heavy than the spotlight. So spotlight is cheapest, point light is more expensive. Then I believe the rectangular light has even more of a cost than the point light. And the directional light is by far the most expensive light model or light actor you can be using. Generally, you should try to avoid using more than a single directional light in your scene and try to use spotlights wherever you can in order to replace point lights. Here, sadly, we do need the omnidirectional light source, so we'll just go ahead and put the light source inside the light bulb. Let's give this a bit of a source radius to make sure that it actually is correctly enveloping the light bulb. There we go. And now, if we go, this of course looks a bit crazy because we are not currently ray tracing the light. But either by accessing console or just using our control panel to re-enable this, we'll be able to see the light kick in. There we go. And now we can see that we made a point light, which we are using to light our virtual assets. But in doing so, we are not lighting the floor, which means that the AR is going to look very detached and rather dull, which obviously is something we should always be striving to avoid. We've covered our shadow catchers, but we also have a pretty useful utility called a light catcher, allowing us to catch, guessed it, light. So here I could dump in a plane underneath these new geometries. This plane is going to act as a light catcher. Its purpose is going to be to catch light. And as you can see, it is now catching light from quite a few different light sources. In order to make this a bit more manageable, for this particular example, we only want this to receive light from this point light. So I'm going to select the plane I just created. Let's give it a name so I can just find it. And we are going to use what's known as light channels within Pixeldope. These allow you to basically segment out light sources to different channels, meaning that the light source or object can now only be affected by selected lights. Then I can go ahead and grab this light source over here. Yes. In order to use the light catcher, we also need to ensure that we allow shadows on translucency, which is what allows us to receive both shadows and light on the light catcher. And then we ensure that this light that we're going to be using, this point light, is set to be using channel 1 as well, allowing it to interact with the light catcher. We're also going to need all these geometries to be using channel 1, so they also can interact with the light catcher. Let's see. For now, I'm just going to go ahead and disable the skylight, just so it's very clear what we're looking at. And let's take a look here. So right now I'm not seeing my shadows compositing as intended, so I'm just quickly going to see if I can figure out why I'm not seeing my shadows. You can also do a double check of our settings in the composite menu within the director. Oh yes. The reason we are not seeing the light catcher behaving as intended is because I've forgotten to enable the light catcher in the world settings. As most other things in the world of IT, sadly, the most frequent issues are going to be existing between the keyboard and the chair. There we go. I'm currently going to disable shadows from the light bulb itself. Sorry, and I definitely don't want to turn off shadows within world settings. I was intending to turn that off. The light bulb itself, we definitely have shadows. On this light fixture, we do not wish to have shadows. There we go. I do believe I have some other lights interfering with this. For now, let's just ensure we only have the light source we intend to be examining, so our scene is not as messy. So what I've done now is I let my scene go a bit of control, which does tend to complicate things a bit. So this is set correctly. This is set correctly. Sorry, that should be a light catcher. And these are both receiving the correct channels. There we go. Mm. Okay, we're not going to spend too much more time on this. Let's move on. But as we can see here, we are now correctly receiving both lights from this AR spotlight, as well as correctly receiving shadows from the very same light bulb. Now, I probably messed something up along the way, so we're seeing a bit of a doubling off on light, but that should be fairly easy to tweak. I just think it's time for us to think about moving on, because we see the clock is ticking and we're approaching the end of this seminar. So on that note, let's just jump back to the set as we had it. And let's look at the final step of this particular session, which is going to be virtual characters and how we would go about controlling them. So simply by reloading my level, we are now back to what we had before. We're going to introduce some characters from APAC that we've taken out of their freely distributed Paragon asset pack, which contains countless gorgeously rendered character models as well as assets from their game titled Paragon that you can freely use in all your sets and experimentations. So realize here that my holdout for these cubes were in a different set, so just quickly reintroducing these here. There we go. They're probably actually a smidge too small, so let's scale them up a little bit. There we go. And now we're going to go ahead and introduce an AR character. So we're just going to filter by skeletal mesh. And I believe we can actually filter by, we can filter by skeletal mesh, and we can go ahead and drag in Sparrow. Here we go. So I'm a huge fan of using these characters to showcase, again, doing virtual characters in an AR setting, because they come supplied with a lot of animations and materials that you can easily tweak and parameterize in order to showcase different features within Pixeldope. Now, before we dive in too deep, we can see right away that, first of all, we need to set these cubes to be holdouts again. And then we also need to go ahead and re-enable ray tracing. I think I'm just going to delete the RTX toggle blueprint, simply because it will constantly keep removing my ray tracing settings every time I go into live mode. We'll dive into the setup for the scene and just ensure once and for all that we have ray tracing up and running, and then we're just going to leave it like that. Which is not, of course, not going to work, because I just deleted the blueprint which this action is communicating with. Let's pull this in, go into play, enable ray tracing, and then we are just going to leave it like this for the foreseeable future. Okay, so first things first, we can see here that we've put this physical lamp directly behind both our character as well as our logo. Now I lost my camera operator, so I'm just going to quickly go ahead and frame that. Something we're seeing here is that the backdrop is looking a smidge bloomy, simply because there's an actual spotlight beaming directly into the physical camera itself, but that bloom is not bleeding in over our talent in a correct fashion. Nevertheless, this is something we've built logic to allow us to work around. First of all, I am just quickly going to temporarily kill depth of field just to be seeing a crystal sharp image. There we go, showcasing one of the many useful features of the console, allowing you to quickly turn render features on and off on the fly without having to necessarily adjust physical devices or presets. So we can see here that going to production composite, we have a few interesting options that we haven't really touched on before. Being in linear space will allow us to do things like correctly bleed in bloom from the backplate onto our graphics. We can also use this to bleed in bloom from virtual graphics onto the backplate. There's multiple ways you can go about doing this. The most straightforward one is enabling light wrap from the backplate. What light wrap does is it simply allows you to sort of blur the video feed and bleed it in around the edges of your graphics. It's a fairly simple effect, but it can be very powerful as long as it's used in moderation. You should try to steer clear of having values over 1 in terms of gain. I personally find that values around 0.6 seem to work very well. And what this really does is just gives a bit of rim light, helping blend the background and the foreground. It's notably especially powerful near this strong light source. By turning off the blur and increasing the alpha, we can clearly see that what is actually happening is that we're taking the video feed and bleeding it in on top of our talent. Oh, using this in conjunction with ray tracing can be a bit heavy on our system. So let's go ahead and relaunch back up, but let's for now disable ray tracing as we move forwards. It's worth mentioning that ray tracing is still highly experimental, so playing too much around with it will sometimes give you crashes as you enable or disable features or pull certain render features too high within the editor. To disable it, we'll just go ahead to General Setup and Settings, and now we can jump back into our scene. We can also choose to restore whatever we had when we were rudely kicked out of the editor, but for now we're just going to jump in as we were. There we go. So we can see that we've lost some of the geometries we just introduced, but that's fine, we don't need them for now. We're just going to go ahead and reintroduce our animated character. Let's simply filter by skeletal meshes. The filter system within the contour browser is a great way to very quickly navigate to whatever you're currently looking for. Just going to drag in Sparrow. And we are going to position her directly in front of the light bulb so we can see what we can do about assuring that the bloom is bleeding in across correctly. It's also not nice seeing characters standing lifelessly around in T-pose. So you can just go ahead and go to the details for this animated mesh. We can set her to be using an animation asset instead of standing static. And we could just give her an idle animation to play in loop as we're playing around with our composite settings. There we go. Okay, so we jump back into Director and keep going where we left off under Production, Composite 3D Graphics. Now we've touched on light wrap, and as we clearly can see here, especially if I make it strong, we're simply blurring the video and bleeding it in across our talent, as you can easily see here, where we're just taking this square spotlight and bleeding it in. So we're just going to go ahead and blur that ever so slightly, reduce the distance. It might actually be a bit too much blur. And if we look at our output feed, what this is giving us is just slight softening, especially at the fringes of a model, giving us just a little bit of fake Fresnel effect, really helping softening and easing the foreground into the background. But still, this is not quite enough. So moving on to our effects, we're going to go ahead and enable bloom. And we are going to go ahead and enable convolution-based bloom. So bloom is, of course, convolution-based bloom lets you bloom strong highlights. But what we would like to be doing here is bloom from our video onto our talent. So yes. Give me a second here. I'm seeing here that we are slowly and steadily running out of time. So I think we'll be coming back to some of these foreground, background composition effects tomorrow during the Virtual Studio session, as I believe we have to move ahead and dig into the character control segment just to round out this second session of Pixelpalooza. But we've looked at light wrap, we've looked at how we can use shadow catchers as well as light catchers to help integrate the background with the foreground and vice versa. The last thing we're going to look at now is how we can take a virtual character and control it using fairly simple blueprints. So the character we just were looking at, we also have created an animation blueprint for. An animation blueprint is similar to a blueprint, except that instead of dealing with any kind of data, it specifically is tailored towards dealing with animation logic and state machines. This animation blueprint in particular allows us to control a very simple state machine. For those of you that aren't familiar with state machines, think of them as flowcharts. They allow you to go between different states, these states being different animations, and then you're allowed to go from one animation to a different animation based on conditions and the layout of the state machine. So we can see here that in this particular state machine, we have an entry where you simply dive into the character being off screen. And then we have a condition where we simply change the play speed to dive directly into the idle pose. This is basically how we enter a character. When the character is in the idle pose, we have the option to go to a few different predefined taunts and poses. And all of these have rules allowing us to go back and forth. We can go to the bow animation if we're allowed to do the bow balance. If this Boolean is set to true, if do bow balance is set to true, then we're allowed to go into this particular animation. And inversely, we're allowed to exit this animation if we are currently in this state. And time remaining of the animation is less than 0.2 seconds. Notice that to exit some of these animations, we don't use a different state. We simply say that when the animation is done playing, like here, the time remaining of this particular animation is less than 0.2 seconds. Then we will spend the next 0.2 seconds transitioning back to idle. This is also probably applicable for this handstand. When we are allowed to do handstand, we will enter transition handstand. Inversely, when we want to go back, we simply check if the animation has less than 0.2 seconds left, and then we're allowed to exit. This is true for all of these animations. So creating a state machine is pretty simple. You can just drag out from a state, add a new state, and inside of these different states, you can set rules to allow animation playback. Here I can just search for play, and then I get a list of all the animations that exist for this particular character. But we're not going to set all of this up from scratch. You can see here that in the idle, for instance, we're simply playing the idle animation, whereas underneath the bow balance state, we're simply playing this particular animation instead. So all we need to do for this to function as intended is simply change these different parameters, these conditions, and then the state machine will just blend between these by itself. We can see that we are already in this sort of start idle pose, where we're simply waiting for the rule allowing us to transition to start idle pose. So let's go ahead and build a blueprint to allow us to start interacting with our character. Let's see here. So that means that instead of using a particular animation asset to control this character, we are going to use an animation class instead, which is going to be the animation blueprint. So let's go ahead and create a new blueprint from scratch. This is again going to be an empty actor. We don't really need to inherit any kind of complex character logic. We're just going to build everything from scratch. Let's call this BP Sparrow Controller. We open our blueprint. And the only thing we really need within this blueprint is going to be our skeletal mesh, or our character, so to speak, which we can find underneath our meshes folder. We're going to go ahead and drag in Sparrow. There we go. And here we can see our character. In case it's not clear why we're going through this, we know that virtual characters and digital humans is all the buzz and all the craze these days. So the reason we're covering this in such great detail is because all of this is essential if you wish to have characters that can walk and talk in virtual reality. Even if you intend to use mocap, you're still definitely going to be needing to use animation blueprints and normal blueprints to control your characters. So now we've gone ahead, we've pulled in our character. And again, the character is going to be using the animation blueprint, ABP underscore Sparrow underscore Pixelpalooza. And as you can see, the moment we assign this, she immediately jumps to her idle pose and just freezes there. The next thing we have to do is we need a way to interact with this blueprint, this animation blueprint during runtime. To do that, we're just going to add the animation blueprint as a variable as well, so we can pass messages and start changing the states that we've been talking so much about. I believe we just need to search for ABP, and we'll be able to find the animation blueprint, which we've previously created. We'll compile it, we'll save it, and now we are more or less ready to go. So let's delete this ABP image scene, and let's pull in our actual blueprint logic instead. There we go. Could we possibly zoom out a bit and get a nice full frame? So of course, currently there's nothing happening and there's no way for us to interact with our character because we haven't actually built any logic yet. I believe the first thing we might want to do is say that on begin play, this is an event which is not called manually, but it's fired a single time every time you hit play, basically the moment you go into your studio or into your AR scene. On begin play, we're just going to tell her to start transitioning from her start pose or hidden pose directly into her idle pose. So to do this, we actually have to do a bit of work. See here. let's get back to the begin play logic later, just because it's going to build on a few other nodes first. Let's start with the most basic action we can do, which is going to be to create a custom event called px_enter. The function of this is simply going to be to manually tell the character that it's safe for you to go from your start pose into your enter pose. If you're curious how we know which poses we have, it's not all the poses that are available to the character, but it's all the states that we have defined in our state machine, which you can see here. We have our entry, which is called the moment this state machine starts, putting us in the start pose, from where we are only allowed to go to idle. We cannot go directly to any of these taunts. We have to go to idle, because you can see there's no connection saying that you can go directly from start pose to this emote. So the first thing we are doing is simply making a button allowing this transition to happen. And to do that, all we have to do is start playing back our animation. By default, you see, we have, I believe that's going to be here. The start animation has a play rate set to 0. So the first thing we have to do is say that the play rate of the idle animation that we're going to start with is non-zero, allowing this animation to play. And then, as this animation is almost done playing and there's less than 0.2 seconds left, we'll be transitioning into the idle pose. I'm sorry if that was a lot of information to take in, but we'll just have to run through it to see what this means. So we made a variable, or ABP. Now we actually need to populate a variable before we do anything else, because this animation blueprint lives with the skeleton mesh. As you can see, we have a skeleton mesh here, the character, and the character has an animation blueprint assigned, and that is a particular instance for that particular character. If you think of a typical game, for instance, you might have 20 different character or monsters or copies of a character running around. All of those need to have their own animations, and therefore they have their own animation blueprints, even if those blueprints are based on the same source. So the first thing we're going to do on begin play is populate our variable for ABP Sparrow. Oh. So we can pull this in. We're going to set this parameter. We're not going to read it. We're going to define it on begin play. In order to set it, we need to figure out what is the animation blueprint currently assigned to the character, which is Sparrow. So I'm going to drag in to get a reference to the character, which has the animation blueprint we need. And then we're just going to dig around inside this character. We're going to get the animation instance, which basically grabs whatever the current animation is for a character, whether that is a manually assigned animation asset, for instance, an idle or a specific looping animation. For instance, Dot over here is not using animation blueprint. He's just looping his idle animation. Or it could be animation blueprint, which in this case is ABP Sparrow Pixapalooza. Knowing this, that it's an ABP, we are going to cast this animation instance to ABP Pixapalooza, let's see, Sparrow. And on begin play, so now we are getting the animation blueprint from the character, and we're just going to populate our variable. The reason we have to do all this is because if we don't populate this variable, we will have no way of interacting with the animation blueprint. We can't give it commands because we don't know where it is. So we simply cannot do anything to the ABP. We can't change the states, we can't change play rates, we have no control. But now we do, because on begin play, we populate the variable, and now we can start doing things with it. We're going to pull it in, we're going to get the animation blueprint. And now we can start searching for different actions and events which are defined in the ABP. In the animation blueprint, we've so far only looked at this state machine or animation graph. But there's also something called the event graph, which is very similar to the event graph in a normal blueprint. hence why it's called an animation blueprint. What we have here is just a large amount of different custom events, and all of these can be fired and they do different things. If we trigger bow, we can see that that sets the value of do bow true, which means that we're now allowed to do the bow animation. Same thing, trigger handstand sets do handstand to true. Trigger exit sets do exit to true, as well as sets the play rate for the start animation to 0, so we're frozen at the exit pose. So for now, we're going to start by entering, which means we probably want to trigger, let's see, we probably want to trigger, we actually don't need to trigger anything because if we are ready to enter, all that means is that we need to set the play rate of the first animation to 1 or anything above 0. Because the moment this animation starts playing, it will automatically transition to idle when the animation is done. Luckily, we don't need to know what the animation is. We already have a variable that we just need to change, which is called start enter animation, which is the play rate for the start animation. So let's pull out from animation blueprint Sparrow, search for, we actually need to set a variable. We're going to set the start enter any variable. There we go. And we're going to go ahead and set that to 1. Then we're going to go ahead and ensure that Sparrow is not hidden in game. We want to make sure that she is visible, because later we're going to make logic that allows us to make the character invisible the moment the character disappears or exits. We're not going to set up control panel buttons for this just yet until we're done making a logic. So instead, we're going to enable this checkbox for call in editor, which gives this a little gear telling us that we can click this as a button directly from the editor interface. So preview live, we're going to select the blueprint we just made, Sparrow controller, and we can see that we have a single button. If we click this, we start playing animation, and she automatically transitions to her idle pose. And the really cool thing is we can actually visualize this if we have the animation blueprint open. So let's do this one more time. First, we look at blueprint here, the blueprint here. Click the button. We see that we fire off this variable change. And if we go into the state machine here, ensure that we are looking at the ABP in the scene, we can see that we have transitioned from the start idle pose to this active idle pose, which has now been running for 30 seconds. Now we can just go ahead and add some logic to start triggering these different emotes as well. This is also going to be very straightforward. We can simply make one of them, custom event. We are going to, there's 3 different emotes. There's the bow pose, there's a bow balancing pose, as well as a handstand pose. So we need handstand, we need bow balance, and lastly, we're going to need something we're just going to call bow. These are the 3 different animations we want to be able to trigger on the fly. We are again going to have a reference animation blueprint, so we can change one of these booleans, and we can fairly safely assume that in order to trigger the handstand, we're probably going to want to use the function which we call trigger handstand, which is referencing the event we can see here, or all of these. So we're going to trigger handstand to set handstand to true. For the other actions, like the bow balance, we're just going to trigger bow balance. And for the last one, we're just going to copy paste the animation blueprint reference, and we're going to go ahead and fire off trigger bow. Again, we're going to go ahead and set all of these to column editors so we can do some testing before we go to the hassle of constructing a control panel. So we're going to select Sparrow again. We're going to fire off First, we have to enter. We cannot go to any of these unless we're allowed to enter first. There we go. Now, as soon as she's done with her idle, we already set pxbow to true, which means that as soon as she's idle and ready to go, she does that taunt action. And when it has done playing, she resets back to idle. We can also try the other actions. We can trigger pxbow balance. Very nice. Dot over to the side is not so impressed. She probably shouldn't be doing that inside. The ceiling height is not tall enough. We can also go ahead and play around with the handstand. See that these are come back because I forgot to save the level. There we go. And that is more or less the blueprint logic we have to worry about. The only thing left to do is going to be an exit animation. So here we can just select these, hit C for comment, and just describe what these do. We can here go ahead and make a new variable for px exit. Which is simply going to trigger an exit. So we'll compile this, we'll save this. We'll have to ensure that the new function I just made is also set to call an editor so I can actually interact with it. Very good. And now, just like that, we can do the full run through. We can bring our character in. Could you move the boxes out of the way, please? Thank you. So we can enter where she goes into idle. We can trigger a particular animation. And then when we're done, we can go ahead and exit. And then to accentuate this, we of course would want to build logic to probably dissolve or animate or hide the character in a more elegant way. But I think we've already gone far enough. We really need to get moving to questions and answers. So the last thing we're going to do is very quickly set up a control panel for this, just so we wrap this up, and then we'll move on to Q and A. So we're going to save this, we're going to close our level, and we're just going to fire up in standalone live mode while we build our control panel. Give us a second to refresh. There we go, we're going to launch it in live mode. And we're going to tab over to director, and we're going to create a new control panel for Sparrow. Create. Oh, just going to go ahead and kill that for now, just to ensure we have better performance and ensure we don't have any unfortunate interrupts as we mess around with this with ray tracing enabled. Let's actually go ahead and enable ray tracing as well, just because we want to wrap this up on a high note. There we go. So again, notice how quickly we can bounce between editor and live. It really is quite spectacular. There we go. So enable ray tracing, and then we can go ahead and you can also see that I have a bit too much light wrap because you can see it's almost like a halo around her. So I will just quickly tone this down because I left this at the showcase values rather than values I would be using in a realistic scenario. There we go, that's something I'm pretty happy with. And then we can move on to our effects. We can also do things like reintroduce noise. We can add a little bit of chromatic aberration to match the distortion in the physical lens, or add vignettes effect to prettify our graphics if that's something we are interested in doing. Okay. So now we're going to go ahead and create our new control panel for Sparrow. Edit. We're going to add simply a few different triggers. These are going to be Sparrow enter, which simply is going to reference the control blueprint. And here we can see all the functions we just created. So we just hook this up to PX enter. Nothing else we need to do. We're done with this button, and then we just quickly iterate our way through like this. We have the Sparrow bow, which is the bow pose. Sorry, that's going to be PX bow. There we go. And the main reason you would want to create a control panel like this is obviously so your operators can interact with the graphics whenever you are going live or in rehearsals, or just to have a way to interact with things in your scene despite being not having access to the editor interface. It's worth mentioning that we could also have a single button trigger multiple actions at the same time. So far we've only been looking at how do we trigger these actions one by one, but there's nothing stopping me from having say a single button that immediately enters Sparrow and makes it do a handstand without having to click 2 button presses. So I could here, for instance, say I want to trigger first enter, and then I'm also going to trigger handstand with a single button press. You can have any amount of targets connected to a single button at any given time. The last one is going to be Sparrow exit. And just like that, we have more or less created our control panel interface. If we were to make this a bit more beautified, I probably would have combined enter and exit to an on-off switch, but that would require a bit more blueprinting, and I don't think we have time to do that today. So now with our blueprint active, I can go ahead and start clicking some buttons. If I hit bow or bow balance, nothing is going to happen, simply because we haven't finished a Sparrow enter first. But if I hit Sparrow handstand, she will enter, finish her idle pose, and go directly to the handstand pose, because we trigger 2 things at the same time. Then if I trigger exit, you'll see here, graciously make her disappearance. And then we are back to the starting point, and then we can just keep iterating and operating the graphics as we please. So I think on that note, we've already gone quite a bit over and we have to answer some questions. So I think we are going to wrap up the AR overview here. And I believe we are going to do maybe a 5-minute intermission to ensure all of you have time to get your questions in. And then we will do a Q&A session. So it's currently 12:26 p.m. So we'll be reconvening at 12:31 to do questions and answers. So I'll be seeing all of you in a bit. Okay, everyone, and we are back. I'm going to give you half a minute or so to ensure that you have all your friends and family gathered around. Call back anyone who might have taken off for a coffee or similar distractions, and then we will start answering all your questions. So I see it's now 12:32, so I think we're just going to go ahead. So we'll start by taking this from the top. So the first question is there any way of using a camera with a non-SDI input, like let's say a USB camera, to get the captures? The answer to that is for camera input and chroma keying, you definitely need an SDI input, sadly, because you will need an SDI input to an AJA input-output device or card. We support the AJA Kona 4, the Kona 5, the Corvid 88, the Corvid 44, as well as the AJA IO 4K Plus. There is, however, for debug purposes, there is a way you could use a webcam as an input through the Unreal Engine 4 Media Framework. In order to get this up and running, there is the guide you've been linked, but basically for all of you who are interested in doing this, please review the Unreal Engine 4 Media Framework documentation available from Unreal's own documentation on their website. Next question is, how do we match and measure the virtual object size with the virtual world? So within Unreal, a unit inside Unreal is basically 1 centimeter. If you measure a virtual object to be 300 Unreal units high, that means you know that that virtual object is going to be 3 meters tall. And inversely, if like here, we needed to measure how tall the boxes were that we put out to make shadow holdout geometries, we measured those boxes to be 19 centimeters across, and then we just created a cube within Pixeldope. The native and real cube is 1 by 1 by 1 meter, and we just scaled it to 0.19. So for these all the basic geometries within Unreal and Pixeldope, like the cube, the cylinder and such, have basic measurements of 1 meter. Next question is, can any actor become a reflection capture actor in the same way that any actor can be converted to a shadow capture actor? Is it possible to adjust translucency of the material in a reflection capture actor? Say, for instance, if we only wanted to see reflections along the Fresnel of an object. Yes, any object can capture reflections. I also now realize that we haven't actually covered reflections at all, which is it's a bit of a crime, actually. So let's do that right now. That's a very, very good question. Banana sticker for you. So we're going to hop into the editor and we're going to do a cursor glance at reflections and how we can control them. Now, as you might have seen, we have a pretty rough, coarse carpet floor here in our office. But for now, let's pretend it's a very shiny, reflective tile or something similar. And we are just going to go ahead and give the floor a reflection. To do that, there's many ways of doing it. You can use ray trace reflections, you can use squeeze-based reflections. Unless you're going to use ray tracing, the most typical way of doing reflections on the floor would be using a planar reflection actor from the Modes tab. Dragging this in, we can see now that we already have a bang-on reflection of our talent. We are then going to go ahead and go into world settings. We're going to search for reflection to ensure that reflections are enabled and that things are reflective. Then the last thing that we need to do is ensure that our floor, our virtual floor, our shadow catcher, is also reflective. There's many ways you can go about doing that. I will simply, for now, I really shouldn't be changing engine content, so I'm actually going to make a new material. I'm just going to copy this from engine content, paste it in my dev folder. Give this a second. And we're going to make the floor reflective and start playing with it in different ways. So here I'm just going to select all the different geometries used in our holdout. And we are going to change this material on all of them, all the different surfaces at the same time. This one, and this one, and this one. There we go. Let's call this AR reflection. And let's just go ahead and give this a smidge of roughness so we can kind of see what's going on. Let's make it perfectly reflective. This is the most basic way you can go about getting reflections into your AR scene on the fly. Make sure that your shadow catcher is actually reflective, as we see here, and ensure that you have reflections enabled in the world settings. And now if I am to go into play mode, we can see that we are now currently reflecting both our talent. We can see dot on the side casting reflections. We're also reflecting the trees and everything else. Could I possibly pester you to move the camera around a little bit? Now we have enabled a whole lot of new render features. We also have planar reflections, which are very expensive. And bringing up my GPU visualizer by hitting Control-Shift, we can see that we are currently not really hitting our target frame rate count, which is why we might be seeing a bit of stuttering. But generally, that's not what we're looking at right now, so we just focus on the reflections, which are looking pretty good, albeit a bit low resolution. That is very easy to remedy by grabbing hold of our planar reflection actor. We can move on down to the reflection tab under details, as you can see here, planar reflection. There's a little arrow you can expand to show the advanced settings, and we're going to go ahead and set the screen percentage of our reflection to 100%. And now if we jump into live, we can see that the reflections are a lot more crisp, sharp, and accurate. We can then go into world settings, search for reflection, and if we wish, we can start pulling them down. Let's say, for instance, that we just want a hint of reflection, like so. It's easy to use these sliders to adjust both the reflection alpha, which is meant to be hiding whatever is behind the actor being reflected. Because if you just have the reflection itself, it will become additive, which you can see, especially on the left side, doesn't look good. You really need that alpha to also reflect the dark spots of your talent. Now, we can also go ahead and break up this reflection in quite a few different ways. There's a lot of interesting things you can do with your reflection actor. We could, for instance, go ahead and give the floor a normal map. So we could go into our AI backdrop. We could search for a normal. We could just go ahead and grab something tiling, of course, like this. Let's grab something a bit more noisy, like, let's see. Probably not this plaster. We definitely want something tiling. Let's just grab this detail normal map, which just has a bit of uniform grunge and noise. So here we can take this normal, this detail normal. We are going to inject that into our material. This should definitely not be docked there. Detail normal, there we go. And we can pipe this into normal to give our reflections a bit of a breakup. By saving this, we should immediately see that our reflections become a lot more coarse and bumpy. There we go. That was probably a bit over the top. We can see that bumpiness is a bit too large scale and is also a bit too intense. So we're just going to go ahead and hit T, not T, sorry, hit U to add a UV or texture coordinate node. We are going to hit M to add a multiply node, allowing us to scale our UVs. And we're just going to right click this secondary input and promote it to a parameter to allow us to have a variable allowing us to tile this normal map. Let's start off with a pretty aggressive tiling of 100. And saving this, we should see that the bumpiness in the reflection becomes a lot smaller. There we go. But we can still see that it's still far too intense. So we can offset this by using a flatten normal node to make the normal map less intense as well. We pipe this in and we just set the default value to be 0.95% flat. Sorry, be 95% flat, which means that we're almost calling the entire normal map. And there we go. Now we have a breakup on the ground, which is not too intense. Flat normal can also be used inversely. If you set this to like -2, we're actually doubling up the normal instead of making it weaker. Set to 1 will completely crush the normal. So let's say we want to do this based on a Fresnel, because many surfaces become shinier the more you look at them from an angle. So then we can, of course, use a linear interpolation or lerp node by just holding L. We are going to lerp between, let's say, 0.26 and 0.3. These are values I find to work pretty well with roughness for our AR reflections. We're going to blend between these using Fresnel. It always catches me a bit off guard how aggressive you have to be with your edge Fresnels to make them only really kick in at an angle. So we're going to go ahead and set the exponent to 10 for now. We're going to pipe this into our alpha here. So then the more we get towards the angle, the less roughness we're going to have, which is the inverse of what we want. So we're just going to go ahead and jumble these values around. So we now jumped into preview live. I'm going to use F10 to decouple from tracking. So we're going to see the graphics moving independently of the tracking data. And we can see here as we go low to the ground, the reflections really become stronger and kick in. And the higher we go, the weaker the reflections become until they're pretty faint. I could even make this more aggressive. I could say that instead of going from 0.3 to 0.2, I'm actually going to go from 0.4 to 0.1. Just to ensure that it's very obvious what we're actually doing here. So now when we're all the way down, we can see at an extreme angle, we're seeing the reflections. And the moment we go up, the reflections go away. And this tells me that the values we just introduced were probably a bit too extreme. But to summarize, yes, we can use every kind of material attribute to change the behavior of our reflections. You could even do more interesting things like if you're having a shiny, bumpy floor, you could take in the video feed as a texture in your material, like so. We could go to our engine content. If you need to access engine content, go to view options and enable show engine content. We can grab our pre-compositing, which basically is our raw SDI input. It's a pretty cool little texture. In case you're wondering, this is far beyond normal use of Pixeldope. This is more sort of what you might do in a very particular edge case, but this is not really standard functionality. This is more to showcase that you have the freedom to do anything you like if you so choose. So here I can take in the actual texture. So I can get the texture of the floor. If, for instance, the floor is slightly bumpy linoleum. And then I could start making shader logic to basically take this image, convert it to a height map, convert it to a normal map, and then I could use that as a normal map for my reflections. This would allow us to get correct reflections and the correct breakup based on the physical look of the physical floor. So if there's a crack in your linoleum floor, for instance, that would show up in your AR reflections. I would like to extend a thanks to some of our friends over at NAP in Amsterdam who taught us this very useful trick. I'm not going to go through all the steps of doing that simply because it would take a bit of time and we're already quite a bit far over. Next question. Is there a way to see all the objects that have been converted to things like AR shadows in case we ever forget or pass the project to someone else? Yes. The custom stencil mask value indicates what type of object an actor is, and you can at any time visualize the different stencils. So here, if I jump into preview live, I don't actually have to do that even. I could just go to world settings. At the very top, you can see that we can change our visualization mode to see the different stencils. So here, for instance, if I choose to jump to shadow, let's see, I believe it's going to be, yes. For instance, Virtual Studio Alpha, I can now see all my different actors in the scene, and I can see tinted blue are all my shadow catchers. These might require a bit of experimentation to understand what all of these different buffers mean and what they do, but this is basically how you can visualize everything happening on every custom depth stencil and every render layer in our composition pipeline. You can also, of course, select an actor, go to the details tab of it, search for stencil, and the custom depth stencil value will indicate which what the actor has been converted to. 1 is default for any object in Pixeltope. It blocks the video feed, so to speak. 2 is a shadow catcher. Setting this to 2, you'll see it immediately in my output changes it to a shadow catcher. 4 is free. It used to be garbage matte. 8 is a mask channel, which is used in very specific, particular edge fringe cases. You could consider 8 to be deprecated. 16, if something is set to 16, it's going to be a Virtual Studio composition plane, basically used to project video onto, as you can see. 32 is for translucent objects, things like glass, things that require to be comped in a different way. And 64 is for ambient occlusion mask objects. Send this to 64 is you will allow us to mask out ambient occlusion, but also requires some other parameters to be changed. And the last one is 128, which is used for augmented reality holdout objects, as seen here. But as I just mentioned, you should not be setting these manually. We're just showing those so you know where you can find it, but you should try to be converting by just using the right-click menu. Next question is, hello. Is it normal that the cylinder is front of the 3 boxes? The real shadow is always present on the floor. Why isn't the mask taking the shadow? Well, I believe we did cover that. We showcased that once you add a holdout geometry or a holdout cube, you can use that to make sure that the cylinder is behind the 3 boxes, including the shadow. If you want to see that again, if you missed that part, we will be distributing the recordings of these sessions at some point later in one of the following next days. So you can review the segment where we covered holdouts at that point in time. Next question is, where can we get the trial versions for learning Pixeltope? Please just get in touch with the person or the sales representative that put you in touch with us or gave you access to this webinar, and they can probably help you out with evaluation licenses. Next question is, how many channels can I use with Pixeltope in the same time? What's the total duration for each clip in HD? There isn't really a fixed number. If you're taking in video feeds as SDI, you're going to be limited by the number of physical spigots or cable inputs that you have on your particular APAC card. If you have something like a Kona 5, then you are going to have 4 inputs and 4 spigots, which has to be used for both input and output. Whereas if you have a Corvid 88, then you're going to have 8 spigots, which means you could, for instance, have 1 input and 7 outputs. But if you're using video files played from disk or over the web, using the media framework, either the Unreal Media Framework or our media input-output pipeline, then there's not really a hard limit. You're only going to be limited by the specs of your machine, the speed of your hard drive, as well as your GPU. If you're wondering what I mean by physical spigot, if you look at this picture, this is the connector slots of an APAC Kona 5. And as you can see, there's 4 input-output spigots. This is what we're currently using. We're out inputting video feed on 1 and 2, which means we can use 3 and 4 for output. The R is just for reference signal, which doesn't really support video. Next question. Is there a way of using a camera with I believe we covered that already. We're using camera instead of SDI. Let's go a bit further down. Do you have a library with a list of all the references of lights like you have for the lens or the tracking systems? No, we do not, but Unreal Engine 4 supports IES light profiles. Many manufacturers of physical lights also provide IES profiles for those lights. This means that you can go to the manufacturer for your physical spotlights and get the IES profiles, which you can use for your virtual copy of those same lights, ensuring that your AR graphics is lit exactly the same way as your physical set, or physical talent if you're doing a virtual studio. Next question is, how do we manage reflections of graphical objects? We just cover reflections, but I'm glad there was quite a few of you who asked about that, because I did miss that. Next question is, which formats do we accept and which one is better? I'm assuming this is in regards to video formats. For video playback, we generally recommend using H.264 encoded video files in MP4 containers. If you need to use alpha in your video file, then you can use the HAP codec, but keep in mind that this is still an experimental feature, so it can be a bit more clunky to use. If you have a very fast disk and a solid rig, we also recommend considering using image sequences, for instance, EXR sequences or PNG sequences, instead of using video files, simply because this will allow for far better quality with no compression. It also allows you to do things like changing your playback behavior in more ways, like for instance, playing your video backwards, which quite a few of the video file codecs within Unreal does not support. Next question is, sorry, I believe I missed the part between creating an Unreal project and connecting to the director screen. Is it possible to see how we connect these? Let's see here. Let's see if I can. So if I understand this question correctly, how do we create an Unreal project and tie this to the director screen? The way this is done is through the director. So as long as you have a data hub up and running, which you do in your setup, settings, network, ensure you have data hub up and running, then all you have to do with your Unreal project is launch it through Pixeltope. Go to launch. You can add your project folder, which should be your Unreal project, and then you can launch any of the levels in your Unreal project. Once you have done this, there's nothing more you have to do. You're already going to be connected between Pixeltope Director and the Pixeltope engine. There's nothing you have to expose. There's nothing else you have to set up. As long as you launch your project from the Pixeltope Director interface and the data hub is running, your editor and your Unreal project will be connected to Director. Next question is, was also about the cylinders, which I believe we've covered. And I see now that we're approaching almost an hour over, so I'm afraid this is going to have to be all the questions we had time to cover today. Thanks to all of you for staying with us, and we hope this webinar was useful to all of you. Before we wrap up for today, let's just take a quick look at what we'll be doing and covering tomorrow. So tomorrow is going to be Virtual Studio Basics, and that is going to be covered by my very talented, great colleague, Jonas Bexan. He'll be covering a Virtual Studio overview from A to Z, similar to what we did today, how you will start setting up a Virtual Studio project, how you'll be building it, how you'll be injecting your talent. He will be covering how to use all the different Pixel actors, like the internal composition plane, as well as the camera route and the track camera and virtual cameras to navigate around the universal sets and ensuring they work for whatever you wish to do. And if there's time at the end, we'll also be covering set transitions using virtual camera moves and different ways of jumping between sets, similar to what we had a sneak peek at yesterday, as well as what you can do with augmented reality and Virtual Studio if you combine them, which is a very exciting subject, and what this means for your potential virtual productions. So I think that's going to be it from us today. Thanks to all of you for joining us, and I wish you a lovely rest of today. Thank you.